So today's topic is actually a webinar on thermal resistance modelling and how you can incorporate thermal resistance models in SimScale. And if you don't know what thermal resistance modelling is, then that's absolutely fine. Hopefully we're going to go through a chapter in this presentation that will give you enough background to grasp an understanding and hopefully start using them in your own CFD analysis types. So to begin with, I'm going to start with a few introductory slides. So this is me. My name's Darren Lynch and I'm an application engineer here at SimScale. I'm experienced in CFD and engineering design, and I studied aerospace engineering at Brunel University. And I've been with the SimScale team for a couple of years now. Who we are. So who is SimScale? So we were founded in 2012 and currently we've got offices in Munich, Boston and New York. We've got more employees also. We've got 80 plus employees actually across the world, and we cover 6 different time zones. And if you're actually interested in where I'm sitting right now, that's little old me in the UK there. We've got 150,000 users worldwide, and together they've created more than 30,000 simulation projects. And to kind of grasp what that actually means to you, a lot of these simulation projects were created as public projects. So if you start picking up the SimScale platform today and you're not quite sure where to start, then you can just pick up one of these public projects, use it as a template for your own analysis. And that kind of really shows you a kind of power that you get from using the SimScale platform. So what do we do? So SimScale was the first company to produce a fully cloud-based engineering solution. So we provide fluid dynamics, computational fluid dynamics software, solid dynamics and thermodynamics. And what you tend to find is people use the term cloud-based very loosely. Here at SimScale we do not. So we've got a browser-based solution. You don't have to download any software. You don't have to have anything stored locally. You can actually just log into the browser and perform the analysis that you actually need to do. So the kind of process that you take to perform a simulation on the SimScale platform is pretty straightforward. And I'm actually going to be taking you through the SimScale platform later on and showing you how easy it is to set up one of these simulations. But a general overview is that you upload your CAD. You're expected to do some sort of geometry preparation or creation first, upload it to SimScale platform. You can then mesh it, set up the simulation, and then analyze all of those results on the platform. So without ever having to leave your browser, you've got a simulation solution from beginning to end. So that's the introductory slides over. Hopefully if you didn't know anything about SimScale, you now do. And if you didn't know anything about us, likewise you now do. But the core of this presentation is going to be on this particular topic, and this is thermal resistance models for SimScale. And I'm going to start off by going through some background. So why would you actually need to use these models? And then I'm going to take you through how to calculate them, how to define them, and finally how to put them into SimScale. So when would I need to know about thermal models? So you would need to know about thermal models when you're carrying out some sort of thermal analysis calculation analytically. So for example, if you are designing a PCB and you're in an early design stage, you might do some hand calculations or analytical calculations as part of a program to work out what your temperatures are going to be based upon some ambient temperature. But also, if you wanted to do a more detailed design analysis, you can then move to CFD. And what we can actually do is we can incorporate these thermal models into our CFD analysis to really get a more detailed, more accurate design analysis to be able to further your designs. So at the moment, we've talked a bit of an overview. We've talked why we might need it, but we don't really know what we're talking about yet. So why would a thermal resistance model be used? So let's take a step back. why would we not go for this model up on the top right? To get the most accurate results, what we would actually want to do is model this component to the most complexity that you possibly can. So that might include, in this case, having a die, having a casing, having leads, a PCB, and all of these different parts of this single component is going to have a different material, a different geometry, and that's going to be, if you know anything about CFD, it's going to be quite hard to A, mesh, B, get converged results, get a good quality mesh to get convergence at all, and also depending on what you've actually defined, you might not get accurate results still. So this is still a model. So if you were to do a detailed model, you've drawn some conclusions already. So when we're doing a detailed model, and that is putting into the CFD software as much detail as we possibly can, we've said, okay, what is actually going to be making a difference to our results, and we're going to incorporate those. But why wouldn't we want to use that? And the problem comes when we've got a PCB. So we wanted to analyze a PCB in a computer and it has hundreds of components. To actually model a component at this level of detail, then that's going to represent a problem both in terms of compute time, because bearing in mind the more complicated you make your simulation, the more money you've got to spend to solve it. And even if you weren't using the SimScale platform, time is money. So if you're spending a lot of time solving a simulation that could be represented in a much simpler way, then that's going to cost you money. So what are our options? How could we simplify this to make it cheaper, to make it faster? But we kind of need to keep accuracy. So we've got two options. We can go for a simple model or a resistance model. So those are just two names, and we don't really have to worry about what they are right now. But let's just bring in an overview definition of what each of those are. So a simple model might be plonking this cuboid into your CFD simulation and assigning a material to it that might be of high conductivity. So that might be assigning some arbitrary material, but we could assign copper. And then we could say that the power that it's dissipating is going to be assigned as a volume on that entire region. And that is what we call a simple model. It's got no discrimination about where the heat is going. All the surfaces are going to be approximately of the same temperature. And that's going to apply the correct amount of heat to the system. So if you're looking at it on a system level, then this might be a good model for you. So you're looking at how much air is going in, how much heat is going out, and what mechanism heat is going out. It might be conducting through the sides, it might be going out the duct. But when might this not be a good model? A lot of the times when we're looking at PCBs and components, we want to be drawing conclusions about the temperature inside that component and making sure that it doesn't exceed some temperature. When it exceeds that temperature, we're going to say, okay, now it's failed. This simple model, when everything is kind of assumed to be one temperature, is not going to be a good indicator of when something might fail. But we have got one final solution available to us, and that is what we call the resistance model. Now, this doesn't model it as one uniform temperature. What it does is it takes into account some sort of thermal resistance between the junction, and that is the junction is what we're gauging to see failure, and it's going to say there is some resistance between this and all directions that heat could flow out of. And when we talk about all directions that heat could flow out of, when we're talking about components, we mean the case temperature, so that's the top face. We mean the board temperature, and that is the interface between the component and the board, and the side of the cases. So that is the resistance between the junction and the sides of the case, and therefore the side temperature. If you look at this, we're going to say, okay, we've got these resistances, these different temperatures, and what we're actually assuming in the resistance network model is that each of these sides is just going to be of an average temperature that is calculated from CFD. And it's going to use these resistances to find out what this junction temperature, that is actually wrong, so that should be junction temperature there. So this point in the middle, this arbitrary point in the middle of the component, is to be the junction temperature, and that is what we would use to gauge whether this component had failed. And we would get that temperature, that maximum temperature that it can go up to, from some sort of manufacturer data. So what is a thermal resistance? So a thermal resistance is very crudely the ratio of the temperature difference between some point and another point divided by the power that is put through the system. So if we turn that into something physical and something that we can understand, we could say that we are applying some power source on a face through a plank of wood. And this plank of wood has some thickness, and we measure the temperature on one side of the wood and on the other side of the wood, and we would know what the power is going through this system. So we're going to assume perfect insulation. We've got no power going back out of the system or through the sides. We're just going to say that all of the power that we're applying to this plank of wood is going through the plank, and we're monitoring the temperature at one side and the other. And the resistance is the difference of the temperatures over that power. So the unit is Kelvin per watt, and a thermal resistance is similar to electrical resistance, where the heat flow is being restricted, and as a result the temperature gradient is present. So that is kind of an analogy to voltage, potential difference, and resistance. So it's a very good way of thinking about it. But when we're actually talking about components, so electrical components, we have a more complicated system to actually think about. So unlike this plank of wood, we can have power going the other way. So if we had a component with power being applied into its center, we could have power going out through the case, out through the board, as mentioned before, and out through the sides. So we need to apply this to CFD, should I say. We need to have these resistance values. And in some cases, very kindly, the manufacturers give us the resistance values from physical testing. So they would put their component onto a test bench, and they would measure how much, what the temperature is on each of the sides, the top, the bottom, and at the junction, and calculate these resistances for you. And if you're presented with that scenario, then you're in a very good position, because you can then go straight into SimScale and use those values. And a lot of the time, you unfortunately don't get these results, these values from manufacturers. Sometimes you might get some values, sometimes you might get 2 values, but you definitely won't get all of the ones to make an accurate model. So it's kind of up to you to decide whether you want to then do your own testing, or whether you wanted to create a detailed model based upon as much information as you could find about this component, possibly even destruction, to put together a model that will represent it well. And then you could go ahead and test it in a very simple environment, a test environment, using CFD itself. And this is basically what we did in this project. If I just take you back to this slide, I went from the top left, the detailed model. I did a test, I put it through a test environment, and then I implemented the results in terms of resistance values onto a resistance model, and later on I'm going to present you the results, the accuracy that you actually expect to get from this model. I'm hoping that you're going to be very surprised. So I did mention junction temperatures earlier. at the moment a junction temperature to you is some sort of arbitrary point in the center of your component. But what it actually is, it represents the heating element within your component. In most of the components we're actually talking about, that's going to be possibly a die or even a point or source on your die. And this is the value in which you're going to be monitoring to make sure that the component isn't overheating. As I said, you're going to get some sort of maximum temperature that your component can withstand, and you've got to make sure that it does not exceed that. And that is really what we're going to be using in a lot of cases CFD for. So we're going to put your components onto a PCB, a realistic enclosure, do a simulation, and hopefully find out what your junction temperatures are going to be, and use that to kind of gauge whether you've got failure or whether you're well within safety factors, and actually this is going to be a good design for you to go ahead and manufacture. So with all that in mind, we can look at the SimScale platform. Okay, how do we define a component on the SimScale platform to be a thermal resistance network? And I'm going to show you exactly how to do that in the live demonstration. But just to give you an overview of the things that you can define as a resistance network, we've got the table on the left, and that shows you what resistance you can input to that into the definition. And on the right, you've got what you need to assign to that to make it a correct resistance network. So to define what component is going to be defined as this particular resistance network, we're going to assign the top face. So you can see here this assignment is the top face. And on the left here you see what the resistances are that we've defined this component. So the top resistance is this face here. So what you would do to find out that resistance from a detailed model is you would look at the temperature at the core, at the junction, and also the average temperature of the top surface, and use those temperature differences to find a resistance based upon the power that we've assigned. And you would go through this calculation for each of the detailed model faces. And what you actually need to do in the SimScale environment or in your CAD software is actually add this cuboid, replace this cuboid with the detailed model, and that should be a good representation to start your resistance network modeling. But what are you required to do to make sure that this is going to be an accurate model in terms of geometry? So we know that we need to assign the top face, we need to assign these resistances and a power value, but in terms of geometry, how do I represent my my component? So it is actually very simple, and you want to have the nearest and most dimensionally sound representation of your geometry, your components, to be present. So that is in terms of area. So if we have a top area that is of X amount, then you need to have that area approximately cross-section of the top face to be the same as your detailed model. Same with the side face and the bottom face, although typically one cuboid is just sufficient. You wouldn't want this to be a complicated shape. So the geometry we need to upload to the SimScale has got to be a PCB with all of these simplified components on its surface in contact with the board. Next up, for each different type of component, you need to create a new definition of a thermal resistance network and define it correctly based upon manufacturer data, physical testing data, or a detailed model that you've carried out tests in CFD. Naturally, the manufacturer or physical test data is going to provide you with more accurate results because they've taken absolutely everything into account and real-life data has been used to give you your resistance model. Just in the case that you haven't got that data, which unfortunately is quite a few cases, you will go ahead and do this detailed model and use the resistance values from that. So what I'm actually going to do is I'm going to exit out of this presentation. I'm going to show you the test models that we've actually got for you. We're going to show you one simulation that uses the detailed model, and then I'm going to show you how we've set up exactly the same components in exactly the same environment using a resistance network model. And then we're going to hop back to the presentation and show you the key results. And as I said, these key results include a side-by-side comparison of the two models. So let me just show all, and I'm currently located in the detailed model. I've changed the visibility to transparency, and if you actually zoom in on this component, you can see that you've got all the detail that I've deemed to be sufficient. So I've included a die there, I've included the leads, and I've included the casing. And the reason, let me just hide this one. The reason I've actually included these components is because they will significantly impact the results. So for example, the leads are actually located and somehow attached to the die, in which case, because they're made out of aluminium, they're going to be drawing heat out, the heat out of the design and onto the board or the environment quicker. So they are important. The casing is not very conductive, so that is actually insulating to some degree the component, the die. So that's included, and the die is the source itself. Now, if you had more information about this component, then absolutely include it. This is only a test environment, so the idea would be that you run your simulation on this test environment, on this detailed model. You get the resistance values, and then you validate your own calculations. Okay, so by validating your calculations, you make sure that you're getting comparable results between your detailed model and your resistance model, and therefore you can go and use it in whatever scenario you actually deem fit to use it. So you could then from here go on to include this into a complex assembly of all these different components, including say 100 of these components, and you could use the same definition for all of those 100 of the same components. So how do we set this environment up? So to start this process, if we didn't have this information from the manufacturer, how do we start this process? So there's actually quite a lot of standards involved in defining this test environment. Most of those standards come from JEDEC, which are basically publish a list of standards for these test environments for the board, for the sort of scenarios that you put the simulation through or the test through. I can't share that with you. You have to go onto their site, register and view the documents yourself. But what I can say is that I've followed this setup as closely as I can on the platform. So certainly for the dimensions, the materials and the like, everything is very similar to what is defined in those standards. So I've created this geometry in my favourite CAD software. It doesn't matter what you use, but you can create this. Alternatively, this project is now public, so if you wanted to use this as a starting point for your own tests, then just go onto public projects, which is located up here, find this particular project and use that as a starting point, download my geometry, put your component on, and away you go. And what that will also do is give you all of the simulation setup that you require. So from top to bottom, we've got a simulation, and the simulation type that we actually used in this scenario was the conjugate heat transfer. And the conjugate heat transfer is basically, if you've got any experience with SimScale, is the heat transfer type that we use for convection, conduction, radiation, all in one simulation. So it's a very capable simulation, and in this case is very relevant for all of those types of heat transfer. So we've created that simulation, we've assigned the geometry, and we've got some geometry primitives. So in this case, what we've actually said is we want to define a point. So we've got a point that is directly on the die. So when we're solving our simulation and at the end of the simulation, we want to make sure that we've got the temperature reading on the die at the center of the die. And that's what this probe point does. So it's located right here, and eventually we're going to assign it into the simulation to get this temperature readout. We've got a thermal couple. So when we're actually talking about thermal resistances, a lot of companies, rather than specifying the resistance associated with the surface, the sides, the bottom, what they actually do is give you a junction to ambient resistance. And what that actually means is it's the resistance that this test environment goes through that is the difference between the junction and this thermal couple. Very useful for analytical type calculations, not very useful for LCFD. But I've included it in case you're using this detailed model to use in some sort of an analytical calculation. And finally, we've got some cylinder that I've located here. It extends ridiculously beyond the domain, but this is for mesh refinement. So when we finally get onto designing the mesh, this is what we use to refine the plume. SimScale, in case you're not familiar with SimScale at all, or this particular analysis type, SimScale automatically defines contacts. So it knows exactly what is what components are touching what, and basically how we should be transferring heat between those these various parts. So we're capable of fluid-fluid, solid-fluid, and solid-solid type interfaces. And this is all done automatically, so you upload the geometry and it picks it up. So huge headache off your mind if you're familiar with any other CFD software. The model, in this case, it's very important to make sure that we define gravity being in the negative z direction. The fluid in this case is air, and that's assigned to the fluid domain. And then very importantly, we've got a list of solids that these materials have been defined into the model. So copper is actually the contact plates. I imagine these are having very little effect on the actual simulation results themselves. You could choose, in your case, to remove them, but to make sure that I comply as closely as I can to the standards, I've kept them in. Epoxy, this is assigned to the board. However, what I've actually done is I've changed the conductivity. So this isn't necessarily that comparable to the material itself, but more to a board. So what we've actually got here is we've got a conductivity in the X and Y plane that is of 20 watts per meter Kelvin, and through plane, so that's through the board, is going to be a conductivity of 0.346. These are typical values that we can get online. Alternatively, we could do a detailed board if we needed to, but these values should be good to give you a good model of what a board is going to be conducting. And everything else is left as default. A few other things that are assigned is the wood that is actually assigned to the test holder, but most importantly are the solids or the materials assigned to the detailed component. In this case, aluminium to the legs, leads, some sort of plastic to the casing, and silicon to the die. And finally, how we're actually going to assign a power to that die is by selecting the die itself and assigning 5 watts. So that's very much your simulation setup. So you could press run simulation and expect to get some good results from that setup. But what we actually want to do is we want to create the resistance network model from this setup. And to do that, we're going to need the average temperature at the top, at the board, and on the sides. Additionally, we want the temperature at the die, which we mentioned earlier from that probe point. And to do this, what we've actually got to do is some result controls. So surface data, what you can actually see here is we've got case temperature, board temperature, and side temperature. And if you look at case temperature, then that is actually assigned to the face on top, and it's sampling every second, and it's the average temperature. So we could do area integral, but that's not much use here. It's the average temperature. And finally, we've got probe points, one for junction temperature, located straight in the middle, and one for thermocouple. And as I mentioned earlier, that's useful for doing your junction to ambient resistances. So we run that simulation. A couple of hours later, we get some sort of convergence plot that's loaded into the viewer now, and we've got some results. So if I go onto the area averages and I pull up case temperature, for example, it takes a little while to load into the viewer, and there you go, some sort of steady state has been reached, and we can take this temperature to be the case temperature. And doing either some sort of hand calculation, some sort of spreadsheet calculation, you can get the resistances based upon the difference between this temperature, the junction temperature, which is under probe points, and junction temperature. So these two values are going to be your temperature differences that you're going to use. And then you're going to use the power that we input to that die. So power was 5 watts in this case, to divide that difference by to get your resistance. So that will, at the end of that simulation, that detailed model simulation, give you resistances for the top, the side, the bottom. That is exactly what we need to do, but now we need to make sure that we've actually done that calculation correctly, and that, to be honest, we can trust these resistance values to be used in a more complicated model. So what we've actually got is a second simulation here, and I'm going to do exactly the same. I'm going to zoom in right on the board, and we're going to see this cuboid representation of the component. And this is what we're going to be setting the simulation up on to make sure that we've got good, valid results. And in terms of simulation setup, everything is the same, except naturally we're missing some of the material definitions. We haven't got aluminium, we haven't got plastic, we haven't got silicon, because they don't exist. It's modelled. There's no real component, it's a model. And instead of assigning the power as a volume assignment, if we go into advanced concepts, what we've actually got is a thermal resistance network, and that is where we're going to do our complete definition. So this is going to be our model of our component. So we don't have to explicitly model the different types of material or the different geometries, and we don't have to define a power anywhere else apart from in here. So from our previous CFD simulation, we've got the top resistance, the board resistance, the side resistance, and we know that we inputted a 5 watt power to that simulation. And what we've actually done is, if I just stop the selection, hide this this space, zoom in, and then if I go, then we can actually see this is slightly highlighted. There we go, that's much better. This is highlighted on the top face, and this is how we define this model. So we've said this is the solid in which I want you to model. Because you know that because I've selected your top face, and that's all you need to do. And we from here start another simulation. We can do all the same sort of things. What's interesting here is because we no longer need this physical component. What behind the scenes CFD actually removes this as a solid, and it replaces it with our model. And what that means is if we have a probe point in the center, we're not actually going to get anything because it's in the void. There's nothing there to probe. But what we do get is we get a separate set of results for the thermal resistance network. That is done automatically. You don't have to define that, and that returns to you your junction temperature. And using the same sort of definitions we did earlier using the area averages for the case temperature, bore temperature and sides. We can also query the sides of the sides top and bottom of that component. And we can bring all of this into one plot and really query, is this a good model for my situation? Now, if the answer to that is no, and the results are completely different, then I would advise to some degree to go back and check your calculations, because it could be that you've done something wrong. It might also be, and at this stage you wouldn't know, in your particular scenario this might not be an accurate model, in which case you would have to use the detailed model. But that aside, I think in most cases this resistance model would be a good approximation for you. So what I'm going to do now is I'm going to hop back to the presentation, and I'm going to show you these results side by side and allow you to draw your own conclusions. So, key result number 1, comparisons of models. So what I've got here is I've got in blue the resistance model and in red the detailed model. And if this was a perfect model, in a perfect scenario, then these would basically be the same numbers. But just next to it in green I've put percentage difference. And the key result that we're actually going to focus on is junction temperature, because ultimately to find out whether a component's failed, we're going to need to know that this one is under that maximum temperature, and therefore if that was off to quite a lot of quite a high percentage, then this wouldn't be useful to you. But thankfully I did the comparison and the percentage difference was 0.9%. So already there I would say, without looking at anything else, that was a good model. So if I was to do a CFD calculation on some sort of complicated geometry, then I could use these resistance models with confidence to make sure that the components haven't failed. But also looking at the top and the bottom temperatures, we can also see that approximately the right temperature is applied. We've got 4.3% out and 1.8% out. So roughly the right amount of power is going out through the board and the right amount of power is going through the top of the case. And then I come along to the sides. So the temperature at the sides is a little less pleasing, I've got to admit. So about 20% off. But luckily for me, I did write down a few of the assumptions that I made. In this case, what I did is I took 1 point on the lead to be the temperature that I used for the side. And in this case, comparing the average temperature of the resistance model to the point on the detailed model might not have been the right thing. What I should have done is I should have basically did a area weighted temperature on all of the legs, all the sides, and that would have given me a better model. And that might have also reduced, also increased the accuracy of the other ones as well. So if I were you, I would go back to your simulation and test that theory. But for now, I'm happy with the results to say that I could go forwards and be confident that the CFD results with this resistance model is going to be good. I've got a few more slides to show you, but I'm going to give you a heads up. The presentation will be coming to an end fairly shortly, so if you've got any questions, now would be a good time to start typing them, and I'll also set aside some time at the end just to go through those. So looking at the surface temperatures, as you can see, you've got a complicated temperature distribution from your CFD results. You can see particularly so that in the centre of the top of the casing you've got a higher temperature than the sides. And if you make a mental picture of this, because I'm going to go over to the next slide in a second that's going to show you the resistance model, you're going to see how these differ. So, differing results. is that although they are same scales and the temperatures are fairly comparable, so remembering from our chart that the top was about 5% difference, that is visible here, but what we're seeing is that the sides tend to be of an average value, and that is very much expected. So what we've done is we've said, okay, the side temperature is going to be an average value, and we're going to use that and the resistance to find the junction temperature. The top is going to be an average value, the bottom is going to be an average value. So you won't get the same case temperature distributions as you do from the detailed model. So that's something to keep in mind when you're actually doing your CFD calculations. You can't necessarily be drawing conclusions about the surface temperatures when you're doing this resistance modelling. And that's important if you're comparing it to a thermal image. So a lot of technology companies are using thermal images in test environments to really get some insight into the actual results. The problem then comes when they want to reduce the costs, their operating costs, and they want to use CFD. And they go, okay, I've got this thermal image and I want to compare it to I want to compare the CFD results to this thermal image. If you've used a resistance network, then that's not going to be correct. If you've used a simple model, then likewise, that's not going to be correct. If you're after comparing surface temperatures, you've only got one option really, and that's to use your detailed model. But it's important to remember what is important to you when you're doing the CFD analysis. So if junction temperature is the important thing for you, then use a resistance network. It's going to reduce your costs. It's going to increase the stability of your simulations. It's going to increase the robustness. And at the end of the day, that should be all we're interested in. Drawing a line somewhere to get accurate results. And this is for you. So, presentation coming to an end. This is where I say thank you. Question and answer time. Let me just check my my chat box to see if anyone's put their hands up. Okay, first question. You talk about radiation in CHT. That's a new feature introduced recently, thanks. Yes, it is going to be released in the coming weeks, I think. I'm not sure on the exact timeline, but CHTs will be getting radiation very shortly. And if you spied that when I was doing the demo, then you can see that it's already in testing. Next question, will you be placing this video on YouTube? Absolutely. This recording gets sent out to you via email, but also it gets posted on YouTube. And I think that answers my next question as well. Will we receive the video of this webinar after it's finished? Thanks. Absolutely. Okay, I can't see any more hands going up, so I'm going to guess that everybody's questions have been answered sufficiently. Okay, no more questions. So thank you very much, guys. It's been a pleasure presenting to you today. My colleagues will be reaching out with this this recording, and if you've got any further questions to this session, then reach out to us and we'll be happy to get back to you. Thank you very much. Bye.